oxidizing compound in the soil. These instruments, the TIGA instrument and the Viking instrument, both used combustion. So basically they took soil and heated it up. And in the presence of perchlorate, organics would oxidize to carbon dioxide. TIGA saw a low temperature carbon dioxide release, which was possibly from the combustion of organics. But it may also be that it's some species of carbonate that happens to decompose. Oop, why is it doing that? I haven't been backed up since July 28th. Oh my God. Your computer sometimes tells you things you don't want to know. Right, okay, so anyway, so we can't actually assign this a high because we don't know that it was organics in the soil. There's some inference that it might have been, and in fact, a reanalysis of the Viking organic analysis results shows that there's a compound that they detected that actually is produced when perchlorate oxidizes organic compounds. And that compound was detected by Viking, and it was thought to be contamination at the time. But in fact, that might have actually been that Viking saw organics and that they were combusted. So again, we're going to give it a higher score than, but not the highest score. And then finally, is the temperature in the biological growth range? And I'm going to go into a little bit more about that. So here's the temperature. These lines actually are the temperatures that were measured at the surface at different times of the day. So during the warmest part of the day, the temperature got up around 258 Kelvin. During the coldest time of the night, it was almost 200 Kelvin. Well, the low temperature limit of growth is 253 degrees Kelvin. This temperature is exceeded during the day at the surface, but when it's exceeded, the liquid at the surface, or the ice at the surface, is probably gone since the humidity is low at midday, and since even though there are frosts being deposited on the surface, they're deposited early in the morning, and then by the time the temperature gets up high enough, essentially they're sublimating. They're sublimating as the temperature goes up. What this graph is showing is this is showing the depth profile of temperature, and this is a model. So the data, it's anchored by these points at the zero depth. But it is, oh, don't do that to me again. Go away. Okay, so this is a model showing what the temperature profile should look like subsurface. And the inputs to the model are based on the results from the TCP. So the conductivity of the ice and the conductivity of the soil is used as inputs to the model to show what the temperature profile as a function of depth looks like. So this work was done by Aaron Zant. He was the PI of the TCP instrument. And he has a paper out in Icarus in 2008 showing that at high obliquity, the 258 degree Kelvin isotherm penetrates to 75 centimeters depth. Now that's when it's really warm. Currently, at depth, you're down about 215 degrees Kelvin. So basically, the bottom line is that we don't think that Mars is habitable at the present time. We don't think anything is likely to be growing at the present time. But when insolation conditions are higher, like at high obliquity, we think it's very plausible, not just that they're growing at the surface, but that they can be growing down in the ice. They don't get sunlight down in the ice, but they do have the ability to metabolize perchlorate. So chemoautotrophs can be growing at depth. Okay, so put all this together, and what do you got? So basically, this is the evaluation of these individual probabilities for Phoenix: liquid water, energy, chemistry, and the benign environment. their individual values, and then their combined value, which again is the product of the four. And again, MEPAG's recommendation was you just pick these three. I've added the fourth one, but in any case, this is the combined probability, and MEPAG's requirement was the combined probability of these three had to be greater than 50%. Well, that's what you got. There's the 50% line right there. My version of doing it comes out a little lower because you're multiplying four numbers that are less than 1 instead of 3. But by the criteria defined by the scientific community, this site warrants a return mission to search for life. Okay, so how does that compare with other landing sites that have been visited, in particular the Mars exploration rovers, Viking, Pathfinder? A couple of caveats. We're comparing sites that don't have similar measurements. There's no relevant information for many of the factors at some of these sites because the spacecraft did not carry similar instruments. In these cases, if I didn't have information, the factor was left out of the computation for that site. So some of these results are biased in the direction of any information you know is given higher weight. But given those caveats, here's how it comes out. This is just how each of the individual probabilities come out for each of the landing sites. And this is how do we come out in the combined probabilities for each of the landing sites. And what you see is that Phoenix is the clear winner. The next runner-up candidate is the Sinus Meridiani site. And if you don't include the benign environment factor, which is the difference between the way I do it and the way MEPAG recommended doing it, it's not a lot lower. Given the uncertainty of the way this entire thing is done, it would be equivalent. But if you add the benign environment factor, it's way down. Why is that? Well, it gets back to the water activity. In fact, there's been a paper published arguing that the water activity at the Sinus Meridiani site would have been too low to support biology. And this is because minerals were found at the Sinus Meridiani site that are only produced in very acidic conditions. The mineral called jarosite is only produced at pH of 3 to 4, pH below that. So, in fact, this ancient sea that was sitting in the Sinus Meridiani site was an acid cauldron, and it wasn't a very nice place to live. All the other landing sites get actually much worse evaluations than the Phoenix site. So, conclusions. Based on what we know, have measured or can infer, the Phoenix landing site is the most habitable zone of any location we have ever visited on Mars. But even more importantly, the northern plains of Mars are habitable in modern times rather than 4 billion years ago, which is when the Sinus Meridiani site was habitable, if it was habitable. Signatures of modern life, if it exists, are much more likely to be found than signatures of life that were deposited billions of years ago. Any geologist who's done any field work can tell you that. And the ambiguity of the results will be far less. So I recommend, and it's recommended in this paper in JGR, that a future mission to search for life should land in the region explored by Phoenix, and it should search for life. So, what are we doing about that? I am very burned out here on a Saturday morning because I'm deeply involved in writing a proposal to Discovery, which is due on September 3rd. And Phoenix itself was selected by a competitive process in a competition called Discovery. So this is a mission called Icebreaker, and it's a Phoenix follow-up mission. And the key feature of this mission is that it drills. This is a drill instead of a robotic arm. And it drills to 1 meter depth down into the ground ice to reach material that was at the surface during high obliquity. So this is the material that would have experienced these conditions that would have allowed growth to occur 100 days a year. This mission would perform organic analysis using a method that doesn't involve combustion, and it would search for signs of life directly, look for biological signatures of life, using an instrument called the Signs of Life detector. And that's what we're doing. So wish us luck, and maybe we'll actually have a chance to find life on Mars in our lifetime. And that's it. Sure, if you want.
Like 5 minutes of questions.
Icebreaker is being proposed for this round of discovery, which requires launch by 2016.
Lots of luck.
You mentioned something I probably misunderstood, but in hydrothermal vents on Earth, we find the energy source, instead of being photosynthesis, is a kind of chemosynthesis. Did you mention something about chemosynthesis being a possibility underground on Mars?
Right, so that's actually the whole story about the perchlorate. The perchlorate would be the energy source for chemoautotrophy, which is the way that you would be allowed to live underground in the ice. In hydrothermal environments, there are other chemical energy sources that biology takes advantage of.
Sulfur. Sulfur?
Sulfur, but usually one of the members of those chemoautotrophic pairs is actually organic carbon. So there isn't a true independent of the surface chemoautotrophic ecosystem known on Earth, with the exception of one, which is deep in the subsurface, living off of hydrogen and iron, basically. And it's actually not related to hydrothermalism per se.
Thank you.
I think this sort of relates to some of what you just said, but Dr. Ben Bova, in his book from a few years ago, Faint Echoes, Distant Stars, talks about a lot of life that exists like beneath the ocean, in areas where there is no oxygen, and I don't remember right now, but the different life that's down there may not even need water. Have you considered any possibility of Martian life that's in those conditions?
Mars is a very Earth-like planet, and water is the universal solvent for life on Earth. It isn't necessarily the most universal solvent or the only universal solvent for life in the universe, but in temperature conditions like are experienced on Mars, it's the most likely one. Furthermore, the problem with looking for life of a, not as we know it, completely different than anything we've experienced, is that we don't know how to look for it. If it isn't a giraffe and it doesn't walk up to you or start talking to you or something like that, it'd be really hard to come up with a chemical experiment to look for it.
Yeah. Also, I followed the first part of your major conclusion that that the Phoenix had been the let's see, the